Hello students, today we're going to be looking at Chapter 5, Properties of Polygons. We're going to start with the first lesson, Lesson 5.1, the Polygon Sum Conjecture. So first I'm going to grab my highlighter and I'm going to make note of the objectives today. Our objectives are being able to discover and apply the formula for calculating the angle sums in a polygon. And remember, polygons are those straight-edged figures where each side is a segment and those segments connect at an endpoint or a common vertex, and they're only connecting to two segments at a time. We can't have any other segments coming in, otherwise it wouldn't be a polygon. All right, our investigation here, it says, given the measurements of the interior polygons of each of these, the interior angles of each polygon, find the sum. And remember, sum is the total, so we would want to add together all of the measurements that are inside of each polygon. So, so I'm just going to scroll down here, and we are going to total up all of these measurements inside each polygon. Now, I'm not super great at doing all of this in my head, so I might want to grab a calculator. But I'm going to be totaling up each of the three corners in all of these triangles. Now, if you do the math on this, this one comes out to be 180 degrees. I'm going to do the same thing over here for this one. And if you notice, this one happens to have two angles that are the same measure, and that brings us back to the idea of an isosceles triangle, where this one has three angles, all of different measures, and that one would be a scalene triangle. The one on the left here also has that 90-degree corner. That would be a right scalene triangle. And this one, all the angles are smaller than 90, so that would be an acute isosceles triangle. But if we continue this and we add this all up, it comes out to 180 as well. So maybe I'll just put these totals right in the middle here so we can see them clearly. All right, the third triangle over here, 118, 31, and 31. If I add all these together, 8, 9, 10, carry the 1, 3, 6, 7, 8, and drop the 1. So 180 again. So if you notice, all three of these triangles, we have a right scalene triangle, an acute isosceles triangle, and an obtuse isosceles triangle here. They are all totaling 180 degrees. But now we're changing into quadrilaterals. So I'm going to grab a different color and we will find the total of the quadrilaterals. So in this one it would be 90, 105, 90, and 75. And either using my mental math or calculator, I'm going to total those up and it comes out to 360 degrees. All right, that one looked like a trapezoid, and by the 90s in the corners here, it would show that these two sides are parallel. So we do have a trapezoid here. This one is actually a kite, and so you can see the two shorter sides and the two longer sides. Now they weren't marked, but once we get more into the properties of a kite, the angles here do prove that this is a kite. And so I'm going to do the addition on that one. 126. 102, 102, and 30. And if I total all of those up, also comes out to 360. All right, this last one, we have 90, 90, 90, 90. It appears to be a square, but I'm not totally sure that all the sides are the same length, so maybe we can consider this just a rectangle. And if I do 90 4 times, 90 plus 90 plus 90 plus 90, or 90 times 4, that also comes out to 360. So here you can see the three different quadrilaterals all totaled up to 360. All right, got some bigger shapes here. Let's go with this one. 1, 2, 3, 4, 5 sides. They're all at 108. So I'm going to do 108 5 times. All right, I'm going to do some math here. 8 times 5 is 40. 5 times 0 is 0, plus 4 is 4. 5 times 1 is 5. Awesome. I think I did that right. Yeah. All right, so 540 for the total on this pentagon. Let's see, do I have any more pentagons? 1, 2, 3, 4, 5. Here's another pentagon. Let's double check. These ones doesn't have all the same angles, so I gotta write them all down. 120, 118, 73, 89, 140. So if I add all that together, doing my calculator in my head, what do you know? 540 again. Okay, 1, 2, 3, 4, 5. Another pentagon. Well, let's take 113 plus 112 plus 100 plus 98 plus 117. Voila, 540. All right, here's some different shapes. Let me grab another color. This one has 6 sides, and they all happen to have the same angle measurement, so that's an equiangular hexagon. So I'm going to do that 120 times 6 this time. 6 times 0 is 0. 6 times 2 is 12. 6 times 1 is 6, plus 1 is 7. So this one comes out to 720 degrees. 1, 2, 3, 4, 5, 6. Excuse me. This one also has 6 sides, so another hexagon. It's just not equiangular. So if we add 107, 127, 126, 125, and 105, what do you think we will get? That is correct, 720. So we're going to put down the sums here that we figured out based on the number of sides on the interior, or on the polygon, and then we're going to find the pattern using some algebra. Now, a polygon has to have 3 sides or more, so 0, 1, 2, that doesn't really make sense, but because this is an algebraic pattern, we are going to use this table to figure out how to write an equation. So I'm going to start with our triangle, which was 180 degrees total. The quadrilaterals were 360. And if you remember back up here, the pentagons were 540. Now we did do hexagons as well, it's just not on this chart. All right, let's look at the next step. Oh, gotta add in my numbers here. So this was 180, 360, 540, dot, dot, dot. All right, now it says find the slope of your table. Remember, the slope can also be called the rate of change, and it's how many degrees are being added each time we increase the number of sides. So we're trying to figure out how much are we increasing by at each stage. And if I look from the 180 to the 360 to the 540, that's an increase of 180 degrees at each stage. So using this information, we can find the y-intercept. And remember, the y-intercept is your starting value. So what we're going to do is we're going to go backwards and decrease by 180. So 180 minus 180 would give me 0. 0 minus 180 would get negative 180. And negative 180 minus 180 would be negative 360. All right, so our slope here is going up by 180, and our y-intercept is negative 360. So we could actually write a slope-intercept form of this equation to find the total of any polygon, no matter how many sides it has. This n stands for the number of sides. So if you think of the y equals mx plus b from last year, b is our y-intercept, m is our slope. So for our polygon sum formula, we have a slope of 180. We're multiplying by the number of sides. And instead of using x, we're going to use the letter n for number of sides. And you can always add in that multiply in between. And then we're going to be adding on the y-intercept, which is a negative 360. So this is the function of our polygon sum conjecture dependent on the number of sides. Now, you don't have to write plus negative. We could also write it as 180n minus 360. That would also work. Whoops. All right, now there's another way to find the polygon sum based on the number of diagonals. So what we're going to do is we're going to draw in all of the diagonals in each of these polygons. Now remember, a diagonal connects two non-consecutive vertices. So on this triangle, these two vertices right here, they are already connected. So I cannot connect them again with a diagonal. If I go the other direction, our top vertex and our left vertex are already connected as well. So I cannot connect them with a diagonal. And in fact, on a triangle, there are no diagonals. When I get over to the quadrilateral, I can connect this left vertex to the bottom right one because they are not already connected. And then also the other direction as well. Can do the same thing for the pentagon here, but as you see, they'll become more diagonals as the number of sides increases. Whoops, that's a terrible line there, but you get the idea. And if I go down to the hexagon here, this one's a little bit more tricky because there are so many diagonals. I'm going to draw in these diagonals as best I can. Try not to forget any. All right, now I'm gonna avoid the next two here just to see if we can get a pattern started. So this figure here has 3 sides and it has 0 diagonals. Okay, this one up here has 4 sides and it has 1, 2 diagonals. This figure has 5 sides and 1, 2, 3, 4, 5 diagonals. I totally messed this up. Let's start this over. All right, so what we're going to do is now we're going to find the polygon sum conjecture based on the diagonals from one vertex. So we're going to take one corner and we're going to draw all the diagonals from that one corner. All right, so over here on this triangle, here's my one corner I'm choosing. I can't connect it to anything else because it's already connected to both of the other vertices. So this figure has 3 sides with 0 diagonals, and that results in one triangle. I do the same thing over here. I'm taking a corner and I'm drawing in the diagonal. Okay, this has 4 sides, 1 diagonal, and it makes 2 triangles. Starting with the pentagon here, taking one corner, drawing in the diagonals. This one has 2 diagonals and it makes 3 triangles. All right, now just looking at that pattern, we have 3 sides to 4 sides, 0 diagonals to 1 diagonal, 1 triangle to 2 triangles. So you can see that as the sides increase here by 1, our diagonals increase by 1, but our triangles also increase by 1. And if you think back to the information we know about triangles, the sum of a triangle is always 180 degrees. So if we can determine how many triangles are in a figure when we split it with its diagonals, we can say that each of those triangles holds 180 degrees. And if I add up those 3 measurements here in this pentagon, 180 plus 180 plus 180, it gets me to that total of 540. just like we found when we added up the vertex measurements. So down here, with this hexagon, it will have 6 sides, which will be 3 diagonals. 1, 2, 3. And that will result in 4 triangles. If each of those triangles is 180 degrees, 4 times 180 leads us to 720 degrees, the total for a hexagon. So the other way that we can write an equation for this is based off of how many triangles we can split the figure up into. So I'm going to go back to our formula, and I'm going to write another way to find the polygon sum. So what we're going to do is we're going to take 180 times the number of triangles. Okay, so 180 times the number of triangles. Well, how do I know how many triangles there are? Every time I look at the figure, the number of triangles is always 2 less than the number of sides. So I'm going to take the number of sides and I'm going to subtract 2 from that. Now, to check to make sure that this equation is equivalent to our equations above, we could distribute. 180 times n is 180n. 180 times -2 is -360. So this is kind of like the factored version of our black equations above. All 3 of these equations do the same thing. They find the total number of degrees in a polygon. So let's practice. All right, this figure has 1, 2, 3, 4, 5, 6, 7 sides and 7 vertices. So that means the number of sides is 7. So maybe this time I will use the longer equation where we had 180 times the number of sides minus 360. I'm going to need to use my calculator for this one. All right, 180 times 7 equals, subtract 360 equals, I got a total of 900. Okay, so inside here, there's a total of 900 degrees. Now, if you notice, they've got a little m here, and that is asking only for the measurement of that corner. So if I have 7 corners, and they are all marked as congruent, I need to take that 900 and split it evenly into 7 pieces. Okay, so calculator again, 900 divided by 7. Ugh, that doesn't give me a perfect number. So I'm going to make the approximate symbol, and it comes out to approximately 128.6 degrees. So that means corner M here, or all of these corners, in fact, are each 128.6 degrees. All right, let's try example B. This figure has 1, 2, 3, 4, 5 sides. Well, I remember from our previous example that a 5-sided figure must add up to 540. So I need to figure out what I already have in this picture. I have a 95 degrees, 110, and a 90. But I'm missing this corner up here, and I'm also missing this corner here. However, the corner in pink is actually a linear pair or supplementary angles with the 60, which means together they add up to 180. So I'm going to take 180, subtract the 60, and I get 120 degrees for that missing pink corner. Now I have 4 of the 5 corners. So I can take my total of 540 and subtract off the 4 corner measurements that I know. The 95, the 110, the 120, and the 90. Ugh, that's a lot of math. So I'm going to use my calculator again. 540 minus 95 equals minus 110 equals minus 120 equals minus 90 equals. I am left with 125 degrees. And so angle T would be 125 degrees. All right, question C. How many sides does an equiangular polygon have if each interior angle is 156? So I don't know what shape this is yet, but I do know that each interior angle is 156. So I'm going to look at this kind of like problem A. In problem A, each interior angle was 128.6 degrees. To find that, we did the polygon sum formula, and then we chopped it into equal number of sides. So I know the answer is going to be 156. I need the polygon sum formula, and then I need to chop that into the number of sides that are in the figure. So if I can solve for n, then I will know what type of polygon this is or how many sides it has. There's lots of different ways that you can solve for this. You could guess and check because it's not going to have like a weird number of sides. It's going to have a whole number for the sides. Or you could do the balancing method. So I'm going to do the balancing method. And I'm going to get rid of this divide by n by multiplying both sides by n. My n's will cancel on the left, and on the right I'll have 156n. The left side, everything that's remaining just drops down. My next step would be to get my n's on the same side of the equation. So I'm going to take this 180n that's positive, and I'm going to get rid of it by subtracting it. My 180n's on the left will cancel, and the negative 360 drops down. Uh-oh, 156 minus 180. 156 minus 180. Well, that gives me negative 24 n's remaining. Now I just need to get n alone. So that means I need to get rid of the coefficient in front of the n. And this is a multiply in between here. So the opposite of multiply is to divide by negative 24. The negative 24's cancel. The n is the only thing that's left. And I'm going to take my calculator. Negative 360 divided by negative 24 comes out to 15, which means we have 15 sides, and this is a 15-gon. And that is our lesson. We will summarize this information tomorrow.